Hello everyone. Today I will present our preliminary review entitled Topology Optimization of Structures in Space. This work should be viewed as a focused mini review rather than a fully comprehensive survey. The aim is to highlight the main topology optimization methods, representative space-related applications, and the role of additive manufacturing in translating optimized designs into practical hardware. Space structures are governed by a very strict mass economy. Launching mass to low Earth orbit can cost tens of thousands of euros per kilogram, so every unnecessary gram becomes both a financial penalty and a mission capability penalty. This is why topology optimization is highly attractive for space engineering. However, space topology optimization is not just a lightweighting exercise. Space components must satisfy stress, displacement, vibration, fatigue, and multiple load case requirements. They also need to pass qualification procedures, often following ECSS standards. At the same time, optimized geometries must be manufacturable, which increasingly points towards additive manufacturing. So the key motivation is this. Topology optimization can generate highly efficient structures, but for space application, the design must also be qualified, manufacturable, and robust under mission-specific constraints. This slide summarizes the main families of topology optimization methods. Sync is probably the most widely used approach. It represents the design using pseudo-density values and penalizes intermediate densities to drive the solution toward solid or void layouts. BISO follows a different logic. It evolves the structure by adding or removing material in a more discrete way, often leading to clear 0-1 designs. Level set methods describe the boundary explicitly, which can produce crisp and smooth interfaces, although they may be sensitive to the initial design. More recently, isogeometric and machine learning based approaches have gained attention. Isogeometric methods can better preserve smooth CAD compatible boundaries, while machine learning approaches aim to reduce the computational cost by accelerating or replacing repeated finite element evaluations. The important message is that method selection increasingly depends on the constraint profile, geometry requirements, and manufacturing route. In space applications, the optimization problem is constrained by much more than compliance and volume. Launch vibration, acoustic loading, stress limits, displacement requirements, fatigue life, and backlink can all govern the final design. Another important limitation is environmental realism. Thermocycling, vacuum exposure, and radiation effects are still not fully included in most topology optimization formulations. This creates a gap between academic optimization studies and flight-ready space hardware. This slide presents examples of topology optimization in satellite components and brackets. These are natural applications because brackets are often load-bearing, geometrically constrained, and repeated across spacecraft systems. The SSTL Star Tracker bracket achieved around 40% weight reduction using hollow macro-lattice concepts compatible with support-free additive manufacturing. The APTS bracket shows a small reduction around 6.6% when both stress and displacement constraints are included. This is important because it shows that mass savings depend strongly on the number and strictness of constraints. Another interesting example is the SIMP optimized pads antenna substrate, where a large fraction of the electric material was removed while improving gain. Overall, the message is that topology optimization can deliver substantial benefits, but the reported mass reduction varies greatly depending on design freedom and constraint density. Beyond brackets, topology optimization has also been applied to larger space and aerospace platforms. The LUVMI-X lunar rover arm and rocker achieve approximately 50% mass reduction while remaining within ECSS stress limits. The Space IL lander engine mount is another important example because it connects optimization with actual qualification performance. These examples show that topology optimization is not limited to isolated academic benchmarks. It can influence real structures from rover mechanisms to aircraft components when properly integrated into the engineering design process. Topology optimization and additive manufacturing are strongly connected. Topology optimization often produces complex organic geometries, internal cavities, and lattice-like features that are difficult or impossible to manufacture conventionally. Additive manufacturing offers a pathway to fabricate these geometries. However, manufacturability cannot be treated as an afterthought. If overhangs, support requirements, build orientation, and process constraints are ignored, the optimized design may require major redesign before printing. In powder bed fusion, overhang angle is especially important because features beyond a certain inclination require support material. The key point is that additive manufacturing constraints should ideally be embedded directly into the optimization loop. This can reduce post-processing redesign and help move optimized parts toward qualification. Still, the technology readiness gap remains important, with representative topology optimized and additively manufactured brackets still far below the maturity required for flight hardware. Despite major progress, several limitations remain. First, full three-dimensional topology optimization is still computationally demanding, especially when realistic space constraints are included. Many methods are still demonstrated on simplified or coarsely discretized benchmark problems. Second, the common compliance with volume formulation is not enough for space hardware. Real components must satisfy stress, displacement, buckling, vibration, fatigue, and qualification requirements. Third, environmental effects such as thermocycling, vacuum, and radiation are still rarely included in the optimization formulation. Future directions, therefore, include high performance computing for full three-dimensional problems, machine learning acceleration, multi-scale topology optimization with embedded additive manufacturing constraints, fail-safe optimization for critical propulsion components, and eventually integration with in-orbit manufacturing. To conclude, this preliminary review shows that topology optimization has become an important computational design tool for space structures. Its value lies not only in reducing mass, but also in enabling new structural concepts that would be difficult to design manually. At the same time, method selection should be guided by the full engineering context, that is, the loads, constraints, qualification requirements, and manufacturing pathway. Documented mass savings are significant, ranging from component level reductions to large system level impacts. However, important gaps remain, especially regarding thermal, vacuum, radiation, and qualification effects. Overall, the combination of topology optimization and additive manufacturing appears to be the most promising route for translating optimized geometries into practical space hardware. Looking ahead, machine learning acceleration, multi-scale methods, embedded manufacturability constraints, fail-safe design, and in-orbit additive manufacturing are expected to play a central role. Thank you very much for your attention.